This video introduces the topic of finding zeros. The learning outcomes are to use synthetic division to divide polynomials by x minus a, and to use the remainder theorem to determine the values of p of a, and to linearly factor polynomials using various theorems. The theorems that will help in factoring are the factor theorem that will determine if x minus a is a factor of the polynomial p of x, the rational root theorem, which helps decide possible factors for the polynomial, and the Descartes rule of signs, which tell us how many positive or negative roots a polynomial may have. Before we begin factoring, let's review division, long division in particular. Let me begin by reviewing some vocabulary as well as long division of numbers. Let's divide 3,105 by 4. Setting this up, we put the dividend, 3,105, in the division symbol and the divisor, 4, on the outside of the division symbol. Now we say 4 cannot divide 3, but will divide 31 7 times. We put the 7 on top of the division symbol and multiply. 7 times 4 is 28, and then we subtract 31 minus 28, which is 3. Then we bring down the 0. 4 divides into 30 7 times. Multiply till we get 28. Subtract and we get 2. Bring down the 5 and divide 4 into 25, which is 6. Multiply 4 times 6 to get 24. Subtract and we get 1. This 1 is the remainder, and we will have written our answer to this division problem as 776, remainder 1. To show that the quotient, the answer we get when we divide it, is 776, and the remainder is 1. Later, when we were learning how to do long division, we saw that we could write our answer as 776 and 1/4, where we wrote our remainder over our divisor. Notice that we can write 3,105 as a multiplication of 776 times 4 plus 1, which is our remainder, in this format, as parentheses 776 times parentheses of 4 plus 1, which is equal to 3,105. This format is the quotient, the 776, times the divisor, which is 4, plus the remainder, which is 1, which equals to our dividend, which was the 3,105. Let's use long division on polynomials. Let's divide 3x cubed minus x squared minus 150 by x minus 4. Our dividend will be placed inside the division symbol. Notice that I do not have an x term, so I will place a 0x in its place. Now place the divisor of x minus 0 on the outside of our division symbol. Now we are ready to divide. I like to divide by asking the multiplication question. X times what will give me 3x cubed? We can see that 3x squared times x will give us 3x cubed. So I will write 3x squared in the quotient above the x squared term, and then multiply 3x squared times the divisor of x minus 4, and get 3x cubed minus 12x squared. Notice how I lined up the like terms so that the subtraction will be easier to do. Now when we subtract, we need to subtract both of the terms, so I tell my students to change the sign and change the sign and then add. Doing this will result in no more x cubed terms, a positive 11x squared, and now I bring down my 0x term and divide again. X times what will give me 11x squared? This will be 11x. I write 11x in the quotient above the 0x term, then multiply 11x times x minus 4, and I get 11x squared minus 44x. Change the sign, and add like terms. This will give us 44x. We bring down the negative 150 and divide again. X times what will give me 44x? Write 44 in the quotient and multiply 44 times x minus 4 and get 44x minus 176. Change the sign, and add like terms. We find that we have a remainder of 26. This means that we can write our polynomial of 3x cubed minus x squared minus 150 as our quotient, which is 3x squared plus 11x plus 44, times our divisor, which was x minus 4, plus our remainder of 26. So you want an easier way of dividing polynomials? We do have an easier way, but it is very limited. We can use synthetic division when we want to divide polynomials by a divisor that is in the form of x minus some number a. So let's do the same problem of 3x cubed minus x squared minus 150 divided by x minus 4. But use synthetic division as it meets the requirement for the divisor that is in the form of x minus a number. First, we need to set up the synthetic division by writing only the coefficients of our dividend. This means we have to write 3, -1, 0, and -150. Remember that the 0 is for the x term that the polynomial is missing. So we find that we have a coefficient for the x cubed term, the x squared term, the x term, and the constant term. If the polynomial had the highest power of 5, we would need a coefficient for the x to the 5th, for the x to the 4th, for the x to the 3rd, for the x squared, and for the x term, as well as for the constant term. To complete the setup of our synthetic division, we get our divisor and equal it to 0. So we have x minus 4 is equal to 0, and solve for x, which will give us x is equal to 4. We place a positive 4 in the small box. Now we are ready to do synthetic division by first bringing down the first coefficient, which means we bring down the 3. Then we multiply the 4 times the 3 and place the 12 under the next number, and then we add. -1 plus 12 is equal to a positive 11. Now multiply 4 times the 11 and place the 44 under the next number and add. 0 plus 44 and we get 44. Now multiply 4 times 44 and place 176 under the last number and add -150 plus 176 and we get 26. These numbers that we have been writing down should look familiar. So our quotient for our division problem is right here at the bottom. We just need to add some x's. Since we started with x cubed, we will start our quotient with x squared, 1 power less than the original dividend. Then we decrease by power to get 3x squared plus 11x plus 44. And the last number is the remainder, so we can write our divisor under it to get plus 26 over x minus 4. Now I did this problem to show you a couple of things. One thing we found was that we can now quickly divide polynomials by factors that are in the form of x minus a. The remainder theorem states that the remainder you found when dividing is equal to plugging in a into our polynomial. In other words, if our polynomial is p of x is equal to 3x cubed minus x squared minus 150, we can plug in 4, which is the number that we used in our synthetic division, into our polynomial, and we get p of 4 is equal to 3 times 4 cubed minus 4 squared minus 150. And if we simplify this, this ends up being 3 times 64 minus 16 minus 150, which is 192 minus 16 minus 150, and that equals to 26, which was our remainder when we did our synthetic division. The remainder theorem means that we can use synthetic division instead of plugging in numbers. You will be asked to determine if a value or number, say k, is a zero of a polynomial. This means we want to know that if we plugged in k into our polynomial, p of k is equal to 0. We want to know if a particular x value will result in the y value of 0. We can plug in our value of k into our polynomial, or we can use synthetic division, where we would put in k value into our small box when we set up to do the synthetic division. So what does it mean if the remainder is 0? This means we found a factor. For example, if we divide 3,104 by 4, we get 776 and no remainder. So we can write 3,104 as 776 times 4, and we do not have a remainder to add. What we have found is that 4 is a factor of 3,104, because 4 times 776 will give us the 3,104. The same is true for polynomials. If we find that the remainder is 0, we can write our polynomial as our quotient times our divisor, and this brings us to the factor theorem. The factor theorem states that if the remainder of dividing my p of x by x minus a is equal to 0, then x minus a is a factor of our polynomial, p of x. So, if we had 3x cubed minus x squared minus 176 divided by x minus 4, we can do the synthetic division and find that the remainder is 0. This means we can write 3x cubed minus x squared minus 176 as the product of 3x squared plus 11x plus 44 times our divisor of x minus 4. Then we can use our knowledge of quadratics to see if we can factor the 3x squared plus 11x plus 44 to see if we can factor our polynomial even further. Let's talk quickly about Descartes' rule of signs and the rational root theorems before doing a final example. Descartes' rule of signs says to count the number of sign changes in the polynomial to see how many positive zeros you may have. So for our polynomial of 3x cubed minus x squared minus 150, we see that there is one sign change from the positive 3x cubed to the negative x squared. So we should expect only one positive zero. If we plug in negative x into our polynomial would be 3 times negative x to the cube power minus negative x squared minus 150. Notice that I put the negative x's into parentheses so that the exponent will apply to both the negative as well as the x. When we simplify, we get negative x cubed minus x squared minus 150. And notice that the signs never change, so we would not expect a negative 0 in our original polynomial. Finally, let's talk about the rational root theorem. It states that if you want to find possible zeros, get the factors of the constant and divide them by the factors of the leading coefficient. Our last division problem we had, which was 3x cubed minus x squared minus 176 divided by x minus 4, we found that the remainder was 0. This means that x is equal to 4 is a 0, and that x minus 4 is a factor of our polynomial. But what if I did not know that 4 was a 0? Where would we start guessing numbers? What numbers should we guess to see if they are zeros? To give you some possible guesses, the rational root theorem says that you get the factors of your constant, which is 176 in our case, and those factors are 1, 2, 4, 8, 11, 16, 22, 44, 88, and 176. And each can be either positive or negative, so we actually have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 11, plus or minus 16, plus or minus 22, plus or minus 44, plus or minus 88, plus or minus 176, that need to be divided by the factors of 3, our leading coefficient, and 3 has the factors of 1 and 3. but they also can be positive and negative. So our guesses for rational numbers that can be possible zeros will come to the following list of plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 11, plus or minus 16, plus or minus 22, plus or minus 44, plus or minus 88, plus or minus 176, because these are the factors of 176 divided by 1. But we can also have plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, plus or minus 8/3, plus or minus 11/3, plus or minus 16/3, plus or minus 22/3, plus or minus 44/3, plus or minus 88/3, plus or minus 176/3. These are the factors of 176 divided by 3. Okay, let's put this all together in this example. Find all zeros and factor the polynomial into linear factors, for p of x is equal to 6x cubed plus 19x squared plus 2x minus 3. So where should we start? We start with the rational root theorem so that we can have some possible guesses for our synthetic division. Factors of the constant, in our case the constant is 3, so the factors are 1 and 3. The factors of the leading coefficient is 6. The factors of the leading coefficient, which is 6, are 1, 2, 3, and 6. So our list of possible rational roots are plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 3, plus or minus 1 over 6. Notice that's the factors of 1. Notice that's the factors of 3, which was 1, and I divide it by each of the factors of the leading coefficient. The other set is going to be plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 3, plus or minus 3 over 6. And then again, when we look at our list and we condense it, we can see that our final list would be plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6, plus or minus 3, plus or minus 3/2. Notice plus or minus 3 over 3 is the same thing as 1, and we already have that written down. And plus or minus 3 over 6 is the same thing as 1/2, and we already have that one written down. So we can narrow down our infinite number of guesses to just 12. So which should we try? Let's set up the synthetic division for our problem. Here's our small box, and the coefficients of our polynomial are 6, 19, 2, and -3. From Descartes' rule of signs, we see that there is one possible positive 0. If we plug in -x into our polynomial, we would have gotten p of -x to be -6x cubed plus 19x squared minus 2x minus 3. And we see that the signs change twice, so there are two possible negative zeros. In fact, there may be 0 chance that there are negative zeros. So according to Descartes, you may want to try the negative number, and since we don't like fractions, let's pick an integer number. Let's see what happens if we pick the number 1. Put this into our synthetic division setup, bring down the 6, multiply 1 times 6 and write 6 under the next number, add, and we get 25. Multiply 1 times 25 and we write down 25 under the next number, and we add to get 27. We multiply 1 times 27, we write that number under the next number, and add, and we get 24. So was the number 1 a 0? The answer is no, since there is a remainder. The last number that we wrote down was not a 0. What we did find was a value of p of 1. In other words, if we would have plugged in 1 into our polynomial, we would have found that our answer would have been 21. So we need to try another number in order to find a 0. Let's try -3. Put this into our synthetic division setup, and we bring down the 6 and we multiply -3 times 6 and place the -18 under the next number, and we add. This gives us 1. We multiply negative 3 times 1 and put the negative 3 under the next number and add to get negative 1. We multiply negative 3 times the negative 1 and place a positive 3 under the last number and add. And there we can see that we get 0 at the end. This means that negative 3 is a 0, so that p of negative 3 is equal to 0. This also means that x minus a negative 3, or x plus 3, is a factor. We can now rewrite our polynomial of p of x is equal to 6x cubed plus 19x squared plus 2x minus 3 as 6x squared plus x minus 1 times x plus 3. We can use our knowledge of factoring quadratics to factor this quadratic 6x squared plus x minus 1, and we find the factors for that is 3x minus 1 times 2x plus 1. This means that our p of x is the same as multiplying x plus 3 times 3x minus 1 times 2x plus 1. This is the factor form of our polynomial. If we want to find the zeros, we can divide and multiply by 3 in this fashion, so that we get 3 times x plus 3 times x minus 1/3 times x times 2x plus 1. And we do the same for the last parentheses so that we get 6, from the 2 times 3, times x plus 3 times x minus 1/3 times x plus 1/2. This is the intercept form of our polynomial, because if we set our polynomial equal to 0, we can see that when we set 6 times x plus 3 times x minus 1/3 times x plus 1/2 is equal to 0, we know that x will equal to negative 3 from the first parentheses, x will equal to 1/3 from the second parentheses, and x will equal to negative 1/2 from the last parentheses. This means that there are 3 x-intercepts, one at negative 3, 0, one at 1/3, 0, and the last one at negative 1/2, 0, and that the zeros of p of x are in the numbers of negative 3, 1/3, and negative 1/2. Notice that 2 of the zeros are negative and 1 is positive, just like Descartes' rule of signs said it would happen. You may want to view the example videos for further practice, and this concludes this video.